covers one of these areas that Claudia just briefly mentioned. And Claudia already prepared you for this by saying that, with visualizations, you could basically prove whatever you want if you don't use them correctly. So now it's up to Max to show you how this is done, or to actually teach you how to build visualizations which don't just prove what you need to be said, but are also useful in their own right. To Max, I just had a look at his CV, as you have probably noticed, to remind me of his unique career. I think Max is unique because he, as many successful researchers, sits at the crossroads of different communities. There are many ways in which you could actually achieve glory and success in academia, and this is one option, to reinvent yourself, but also to be able to talk to different communities and different groups and learn their language and be able to present your research and your interests and sell your core competencies and skills to as many audiences as possible. So Max has been brilliant at this. In addition to that, he's one of the most innovative, creative researchers I know in his own right. He is originally from the HCI community, so he's one of the few people I know that actually has papers accepted at prestigious conferences such as CHI. He has spent lots of time at MIT to learn how to do that, actually 10 years for his PhD. I'm sure he can tell you more about this in one of the evening sessions. And among other things, he learned how to build pretty things. And this tutorial is going to be about that. So I give you maximum Kleek on data visualization.
Thank you, Elena. Hi, everyone. So that was mildly embarrassing. I was actually at MIT a little bit longer than 10 years, but we won't talk about that. So I have to entertain you for an hour, and it's a great pleasure because visualization is a really exciting topic, and it's something that is taught in lots of different ways. If you go on the web and go to all the MOOCs that you can find and look at all the visualization courses that are available, you'll notice a huge variety of approaches. Many of them are very practical. But one thing I learned at MIT was you should never be practical first, because people can learn that stuff. That's something you can learn on your own. But theory is something that I think is fundamental to guiding you along the way. So the next hour, which is actually an hour and a half's worth of material, slightly compressed, I have a little knob that you can speed me up and slow me down arbitrarily, will be about cognitive science and about what we're trying to do when you design data visualizations. And so this is the goal of this exercise, is to help you when you do embark on using particular tools such as the R environment, which you'll be playing with this afternoon, as well as the D3 environment, which we'll talk about as well. But anyway, so this is let's get started because I have a bit of material. The first thing we're going to talk about is what I call the biological basis of information design. So we are these creatures that have some interesting properties about how we've evolved. And that makes it it's such that we can see things in certain ways, and it'd be great if we could design things to take advantage of our evolutionary capabilities. But in addition to sort of taking advantage of what we're good at doing, we also need to consider the kinds of goals that one is performing when one is looking at designing visualizations. Finally, you also need to look at the data that you're looking at. So obviously, there are many kinds of data. You might be, if you're not experts on data already, you will be by the end of the week. There are lots of shapes and kinds of data, and we'll talk about a lexicon to characterize that kind of stuff in a bit. And that will affect the decisions that you make around suitable visualization approaches to those kinds of data. But parallel to the kinds of data, you also have kinds of visual approaches to representing the data. So we'll talk about what I call visual dimensions and ways that the whole task of designing visualization is simply mapping. All it is a mapping, right? The world is, in computer scientist terms, are full of mappings from these sort of types of data that you have to visual dimensions. And that mapping choice is informed by optimally informed by the biological basis. So anyway, that's the first lecture. The second lecture is going to be very brief and is about interaction. So we're only going to be talking about representation for the first half an hour. The second half an hour is about actually interacting with data, and I'll basically introduce you to a very simple lexicon so you can talk about interaction in a useful way. And again, the task is very relevant here. A different set of tasks we're going to talk about, and I'll quiz you at the end of that. Okay, friendly quiz. And Elena will be out of the room, so she won't grade you. Okay, so as far as, I didn't come up with any of this. There are at least 30 years of research in visualization. The two books that I hold as most useful, that I highly recommend, everybody asks me, what should I read, are ones that are not frequently recommended, actually, but I stand by them. So if you don't have this book, you should get it. This is Edward Tufte's Visual Display Quantitative Information, and sorry, I'm going to say that you should get it because it is really entertaining to read as much as it is informative. He precedes the sort of computer revolution as far as designing information graphics. A lot of the examples he gives are drawn by hand. But he is a dilettante and all sorts of things, but one of his greatest hobbies was designing statistical information so that it's not distorted and so it's most honest. But he's also an artist, so he knows how to balance the aesthetic element. The left-hand side, though, he doesn't talk much about psychology. So the book on the left, Colin Ware is actually a psychologist, and a lot of the sort of motivation for why I choose different kinds of visualizations when I do things myself comes from a psychological perspective. So this is a really nice book because it brings in the cognitive science. Unfortunately, though, they're very theoretical, fortunately or unfortunately. If you want a more practical approach, the two bends of information design, ones you should take a look at. This is my mentor, Ben Fry at the Media Lab. I worked for him for 4 years. And Ben Schneiderman is the guy who founded the field of information graphics. And he basically put his name on a lot of the techniques we'll talk about today. So let's get started. What is the goal of, in my opinion, or what I think we should talk about, of information design? So somebody says, let's build a visualization of some data. You can go about it in many ways, but I would argue that the most effective way to go about navigating this massive space of possibilities is to use the heuristic of trying to design representations that help people think about data, okay? And that is distinct from, but maybe complementary to, a secondary goal, which is to communicate information, okay? And so, a few examples in which there's an overlap, but they're not necessarily the same thing. And I'm going to borrow a very odd metaphor to talk about this thing. And if there are any cognitive scientists in the room, you can hit me afterwards. But I'm going to use the metaphor of what computers look like, computer architectures look like today, which you may or may not be familiar with, but this is a very cartoonish illustration to make it simple. So in your computer that you have in front of you that you're not paying attention to because my lecture is so engaging, you have a sort of core central processing unit, which is a very versatile piece of silicon that can do all sorts of complex things, right? But it does things primarily one thing at a time, or a few things at a time. It's designed to be multi-purpose and good at doing anything. Back in the past, it used to be that was the only thing that was part of your computer. You'd have this core central processing unit that was responsible for everything. But recently, in the past 15 or 20 years, designers have begun to factor out a secondary little helper guy called the GPU for doing tasks related to rendering computer graphics. The reason is that when you produce the image of a scene, you often do repetitive tasks over and over again for the entire span of the visual scene that you're constructing, right? And so if you design specialized hardware to do that task, then you can do it a lot more efficiently and a lot less power. And so this is a highly parallel kind of architecture that's designed effectively to do one scene at a time. So this is a special piece of silicon that can do a whole scene at once. And now you can imagine the CPU can go off and do other things, right? The reason why I'm telling you about this is that we are kind of this in reverse, okay? If you excuse the extremely crude analogy. So we start on the right here. Our eyes are connected to our visual cortex, which is extremely parallel processing wetware. that goes and instantaneously starts extracting information out of our scene that we see in front of us. Their current understanding of the visual cortex is such that it's very much like a layered architecture. There's an initial sort of set of neurons that are stimulated by the entire field of view, and then we start to specialize. And the specialization actually looks kind of like a computer. You have it's very strange. The visual cortex feeds directly, our optic nerve feeds directly into the visual cortex, which is at the back of our cranium, right here. So this is where the most rudimentary processing of our scene is done. And that rudimentary processing deals primarily with detecting edges and geometric features at the lowest level. And then what you have are two pathways. One pathway is concerned with the spatial arrangement of things out of those lines that it sees. And the other pathway is concerned with object identification. At least that's what the current theory of these pathways is all about. What's interesting is that the closer we get to the front of the brain, the more complex and serial we get. So we have extremely parallel stuff going on down here. And then you get slower pathways that then lead into your frontal cortex, which is where you do deliberative processing, planning, and thinking about things. Okay? And to illustrate exactly how fast this parallel stuff in V1 is, there are many visual experiments that were done in the 60s, 70s, which basically determine how fast you can find outliers that are designed specifically to allow your parallel part of your brain to process. So these are particular fields that have outliers in them that you should be able to detect fairly quickly if you can see the screen. So those of you sitting back there may not be able to see directly. But if we start to do more sophisticated spatial arrangement processing, it takes a little bit longer. You probably can't sense how much longer it's taking you, but these are designed to tickle the V2 pathway that dealt with spatial arrangement. Well, if you then go and design a representation that might not be as fast, then you can feel yourself thinking about things. So these two visual representations are designating the same semantics, okay? Now let you look at that for a second. You can tell me, you can convince yourself that they are equivalent. But one of them is much easier to see than the other. Yeah? Can somebody tell me why the one on the left is equivalent to the one on the right? Someone? Marcus?
Because assume it's representation.
Right, and how long did it take you to figure out that that correspondence was equivalent, right? You probably engaged in a fairly serial process of making that mapping, right? They're both visual, but there's some semantics here encoded and something that you had to unpack. And so obviously, if you use this representation, then you're going to work harder to achieve the same conclusions. And you may not actually, if you had a very high dimensional space, you might not even see the relationship here, right? Whereas if something like this, you'd be like, ah, okay, I know what's going on. I use the analog of Tetris. So if you go and talk to Tetris players, or if you play Tetris competitively, which I'm sure some of you do, and this is a very slowed down version of, well, actually no, it's me playing, so it's in real time. I'm really bad at Tetris. But you'll notice that what people do is they will actually rotate, what professional Tetris players will do is find it easier to physically rotate the piece very quickly and match and figure out where to drop it than to actually mentally rotate these things. So this is called external action. So, and this shows you that this is merely evidence that people automatically optimize for letting their visual cortex do things. So doing things like, for example, matching contours is much easier than rotating the piece in your mind, especially for the evil pieces that are mirror flipped, which our brains are really bad at doing. There's actually another reason why people rotate these things over and over again. That's to figure out which piece it is before it enters into view completely. So why is this stuff important? Why is it important that we can see these things more quickly rather than the less efficient representation? Well, you might have a situation that something really good or something really bad is happening, and you need to figure out what it is, what's causing it very quickly. So you might have a paper deadline, for example, and it's really bad and it's coming along. Or you might have a plague which is hitting London and killing lots of people. Back in the day, you didn't have the luxury of plugging these things into Google Maps and then seeing a visualization and figuring out what you're doing. Probably the most famous example, of course, which everybody knows about probably, is John Snow's cholera map of London. And this was a very interesting case because in 31st of August 1954, there had been an incredible surge in deaths of this mysterious disease that people didn't know what was going on. And the number of deaths was doubling every 3 days. And so it seemed to be doubling every 3 days. The only way they could actually tell this, of course, is by going around the town and knocking on everyone's door and asking people how many more people had died the night before. Not a very cheerful exercise, but John Snow and his colleagues, all volunteer, essentially citizen scientists, engaged this. And one of the representations, so there were multiple competing hypotheses as to what was causing this epidemic. The prevalent one was that there was a bad air coming from the sewers in London, and that was making people sick. And so in order to test this hypothesis, John Snow drew the location of the cholera deaths and the locations of the sewer outlets, which were marked in X's around them. And he noticed that there was actually, I believe the other ones were the wells. So he had another map where he drew the outlets of the sewers. And he noticed there was no real relationship that he could find between the deaths and the sewer outlets. Whilst when he drew the X's of the wells, he noticed that things seemed to be really clustered around a well in the center of the town. And of course, that's the famous Broad Street well, which was found to be contaminated and was killing people. And you notice that with this kind of visualization, people can immediately identify clusters of where things are very dense and also where outliers exist. So with this outlier, this very strange square in the middle, was actually a monastery, and nobody at the monastery had died, even though it was a very busy monastery. There were 100 monks there. And the reason, do you know why nobody at the monastery had died? Sorry?
They had their own well.
No, they didn't have their own well, but
Didn't they make beer?
they drank beer, exactly. They never drank from the well at all. So it was a very interesting story. So, moral of the story is you might want to drink some beer. This is another very famous example of visualization that saved hundreds, thousands, tens of thousands of lives. And this is does anybody know what this is? Harold Hemsworth is the name? No? So this is, he was looking at the steady state glucose response of individuals that had this very peculiar disorder that caused their glucose to drop very precipitously in certain ways. And he used an early form of topological data analysis to reduce the number of dimensions he was looking at to 3, right? And when he did this, it was called perspective chasing. And when he did this, then he noticed that there was a very distinct sort of clustering of individuals who had one kind of response and people who had other kind of response. And those are what we currently identify as type 1 and type 2 diabetes. And so that was an incredibly important visualization that would not have, that would have set back our discovery of the difference between type 1 and type 2. There was immediate response from the medical community to actually looking at whether these were caused by the same problem or not. And so, and now the final example I wanted to give before we dive into the nitty-gritty things of data dimensions is a wonderful example from Florence Nightingale. And this is a number of casualties in the hospitals as there is during the Crimean War. The interesting thing about this one as opposed to the other two was that this was primarily designed to communicate how bad the hospitals were, right? So the blue portions of these triangles were the number of people who died of communicable illness in the hospital. So these resulted of infections that were that people came down with once they were admitted. And the other parts, the areas, are proportional to the number of people that died with the actual cause that they arrived at the hospital for, the black. And so she has a key somewhere. But this actual original is available right now at the British Library. You can go see it. It's on display, and it's an incredible thing. But she did other work pertaining to whether, at what months of the year correlated the greatest to these communicable disease outbreaks in the hospitals. And she knew how bad it was because she was working with all the staff in several of the major hospitals in the war. But she just couldn't get it across to management that this was really important. So she drew these visualizations and to just bring home the point that, all of these people are dying not because of their wounds, but because their hospitals are crap, right? And this was, it took about 2 years for people to actually engage in sanitary reforms to improve the quality of that hospital. But anyway, so let's talk about nitty-gritty things. So now you're the new Florence Nightingale, or you're embarking on a new task, which is to design an information visualization approach for your data set. And say that you have a data set like this, which you probably can't see, but that's okay. And you've just sent your graduate student to, or your undergraduate student, to go collect data, and they've come back with a wonderful table. And they said, okay, well, I've measured all these flowers for you, sir, and these are the dimensions of all the flowers in your garden. And you say, well, that's great, but that doesn't tell me anything, because it makes me use that, the cognitive part of my brain where I have to actually look at these numbers and try to figure these things out. So then I use my extremely sophisticated tool known as Excel, and use all the default options, and I end up with something like this, right? Immediately, what do we notice? So apparently my graduate students had collected 3 kinds of plants, which was kind of cool because I asked them to do 5, but that's not bad. And then there's some weird thing going on here with the petal length. This guy seems to have really long petals, and they seem to be pretty well clustered to those 3 distinct categories. And okay, that's fairly cool. But then I go, because I'm really cool, I put it in my D3 visualization, and then I use what we call parallel sets representation, which we will talk about very shortly. And that shows me something quite different. And this representation really shows me the relationship between so some of the flowers have these sort of chunky short leaves, and other ones seem to have the exact opposite, long and slender leaves, right? And so the parallel sets representation enhances your ability to see the relationships between neighboring dimensions. But what about dimensions that are farther away? Like, what's the relationship between sepal length and sepal width? Well, you have to sort of follow these things through, right? So it's a bit of a pain to do that. So you might want to figure out how to support exploring multiple dimensions. We'll talk about that in a bit. So how do we choose? So why do we choose the Excel version versus the D3 version? And there are actually probably 80 other techniques you can use to look at data. In order to make that choice, we first of all have to talk about what kind of data we're dealing with. So that's what we'll do now. Okay? You can stop me at any time, by the way, if I say something strange or otherwise controversial. Okay? Or if there are questions. So, so let's talk about data types. So you're starting with a data set, and when you talk about a data set, then we're usually talking about a set of data elements, right? Where every data element might be, if you're lucky, integral, like this, or a fixed point, then your age in fixed point years, or alphanumeric, or fractional, for example. They may also be categorical, so it might be the fruit in your basket, for example. Or it could be relational, for example. This data set might just be the number, sort of the friend relationships of everybody in this room, right? And so when you have a data set like that, then your objective is typically to understand or help the user understand or to discover any relationships that may be present among the elements of the set. Okay? But if more than often, sorry, I'm getting ahead of myself. Even for this example, there are many, many kinds of ways that you can look at these things. So you might stick them into Excel and tell it to make a dot chart or a line chart or a bar chart, and that's all great. They're all fairly equivalent in the sense that you can, they tell you your eye about basically the same thing. But you've already implicitly made an assumption that the order of the elements in your set was significant, right? If you reordered the elements, then your eye is already telling you a slightly different story. Right? Of course, if you're a robot, then this representation and that representation are the same. Right? But you want to make life as easy as possible for you, since you're usually not a robot. But so you need to ask yourself: is the ordering important? If the ordering is not important, then is it merely are the elements themselves important, or is it the count of each? So you might want to bin them and count them, and that's what we call histogram. If you have a huge number of points and you just want a summary of where they are and approximately the values, you might want to use something called, which statisticians use all the time, called a box and whisker plot. And all that does is it tells you basically where the median of the data is, the interquartile range, so typically 25% or 75% interquartile range, and the extrema. Whoops. We'll go back. But the extrema are the minimum and maximum elements for each dimension. But more often than not, you are, uh-oh, my remote control is now really hating me, so give me a second. More often than not, you will not end up with a single dimensional data set, but rather each element in your data set is actually comprised of several things. So somebody's really conspiring against you. And you might have, for example, one measurement, or two different measurements, and a categorical element. So each dimension of your data might be a different type. And this is significantly more interesting because your goal here could be the same as the goal from the last element, which is to understand the relationship among the elements. Or it could also be to understand the relationship among the dimensions of your data set. Do you understand the difference? Is that all right? So in other words, in the last exercise, we only had one dimension per data element, right? So we had like the ages of the people in the room, or your grade point average, or whatever. And so your typical task then is to understand or discover relationships among those elements, right? So how tall are people, right? But in this one, if you have more than one dimension, you can interrogate relationships among the dimensions, potentially. So do tall people eat more apples, right? In addition to asking the questions about, well, how many people like apples in the room, okay? So that's what we have to take into consideration when we're choosing relevant representations in our data set. So let's take a very simple example, just like the one that we took for the single dimensional case. So we might, again, bravely take our data set into Excel, which is not a cowardly tool, by the way. Excel is perfectly fine for data sets less than 1,000 data points. And it gives you something like 100 different options of different sort of color gradient shading. But as the result of this lecture, you'll probably be able to quickly collapse all of those examples into basically 5 different representations. And two of the actually distinct ones are whether you want clustered bars or stacked bars. So tell me which representation you might want to use if you wanted to know overall relationships to the total. Which one would you choose?
Stacked bar.
Stacked bar, because you can your eye immediately tells you what the total is, right? Whereas the clustered bar doesn't really help you. Well, what does the clustered bar help you do, perhaps? Compare. Great. Okay. Other options you can do is just treat them as multiple series, so you could draw multiple lines. But because you have, you may be trying to do that second thing that we talked about, which is to compare the relationship between the elements. You can do this wonderful thing called a scatter diagram, where you compare one dimension to the other dimension, and you want to see whether there's any relationship, whether it's linear or hyperbolic or anything. And that is what we'll do in the first practical in an hour. Then there's this creature, which is often used, called the stacked area. Now the thing about the stacked area, which it's used very often, which actually annoys me, is that I find them ambiguous, and you can agree with me or disagree with me because it's not in any textbook. But when you have a stacked area, one of these is a stacked area, and the other one are just two area plots that are one behind the other. And without telling you anything, it's practically impossible for me, or it takes me a great amount of processing time to figure out which one is which, right? I guess this one might be the stacked area, right? Because the totals are higher, but otherwise I would have no clue. Do you understand? These two come from the same data set, right? Except one of them, there are two areas, this one is two areas behind one another, and this one is stacked on top of each other, okay? So if you're looking for the total contour, then this might help you, right? But I would say avoid these things entirely and just use stacked bars to make them really clear, right? And there's an even more evil version, which we'll talk about a little bit later, called the extreme graph. So let's talk about dimensions, and this is one which I love confusing students, but sometimes I get confused myself. So how many dimensions is your data set? So say that you went camping, and you measured the number of apples that you ate every day on your camping, and it was you and your partner, and so you went for D days, right, camping, and you measured the number of apples you ate and your partner ate. So what is the dimension of your data now? You have 50-50 choice here.
2.
Okay. And it's sort of a trick question, of course, because I'm never a nice person. So the answer is it depends, right? So, so if you're comparing days, then how many dimensions is your data?
10.
yeah, D or 10, yeah. And if you're comparing people, well, sorry, did I get that wrong completely? If you're comparing days, then how many dimensions is your data?
2 dimensions.
2 dimensions, because you're comparing both people for all 10 days, okay? But if you're comparing people, then what is the size of your data set? 2, right? But then number of dimensions on each is 10. Okay? So that's why you can't just answer the question, how many dimensions is your data, without asking for what purpose. All right? So this is just a long version of this explanation. All right. So great. Everybody got that? Right. Now, say that you have that same data set, and but instead of going with 2 people, you've gone with 10 people out camping for 10 days and ate lots of apples. Okay? What you might want to do is not figure out exactly the comparison of how many of people, but you might want to figure out whether there were similar people in their apple eating habits, right? And so you might want to measure essentially how similar people are at apple eating, and so you might just want to pass a kernel over these things. So this is just a function that measures the distance between me and somebody else. If you measure me as the number of apples I ate on my trip, right? And so there are many kinds of examples of distance formula you can use, but that was just the Euclidean distance, okay? And what you end up with when you do that is you end up with this very simple table, which is a what kind of data set? What are these here?
Coordinates.
It's showing you the relation strength, right? So it's a relational data set where you have sort of the relational strength of the similarity scores on the right. And you can do all sorts of wonderful things with these relational data sets. For example, I think I have an example. Oh yes, you have, this is what we call a something matrix. What's it called? I believe it's called an incidence matrix, where you basically show, oh my gosh, I've completely gone forward here. Go back. Thank you. All right. I need to explain this example because this is, okay. So what this does is it shows you how similar people are. So every element is both on the vertical and on the horizontal. And the shading of each pixel is representing the strength of how close or similar people are. So what you could do is, if you then sort by similarity, you can end up with this wonderful kind of clustering appearing and popping out at you so that you can quickly identify them. So you see that there are some apple eaters that are very similar, self-similar, and then there are people who are highly peculiar, and that helps you out quite a bit. Another favorite representation for this kind of data set is a force directed graph, and this you will use in the example, which basically uses simulated physics in order to turn the strengths that we talked about in that table into forces, and then things sort of, these are a lot of fun. However, you may actually get more use out of the other example, and I'll show you why. These things don't scale very well anyway, talk about that later. So now we've already talked about data. So we're done talking about data that we know how to measure the dimensions and the size of our data set. We know how to characterize what kinds of data we have as each dimension. Okay? Now we can have fun. We can map each of these data dimensions to visual dimensions. And it turns out that we are evolved to handle a large quantity of different kinds of visual dimensions. So these are all sort of basic things from an art textbook you might consult that have different kinds of properties. So even if we talk about position, which is probably the one that is the most common for us to get started, there are already many different kinds of ways you can map values to position. We can, for example, if you have an extremely large array of ranges, you might benefit from looking at things in a logarithmic view versus a linear view. And we also talked about things where you end up with tons of, if you have a large data set with many things in between, you may want to consolidate things that are within certain ranges so you can more easily compare things in each set. And that's what we call binning, or histogramming with a particular window. And so even with just position, we have a lot of flexibility about how we use position. The great thing about position is that it's very easy to look at, and our eyes are designed to do it very efficiently. The bad thing is that we run out in 3 dimensions. And probably the most basic data sets in the world that you will deal with will probably be higher dimensions than 3. So then what do? Well, you resort to something else, right? So we were talking about orientation already. And orientation is great because it has that pop-out property of quickly being dissected by that V1 area of a brain. However, the disadvantage is that it's range limited, right? A line looks the same when you go all the way around. Triangles are even worse, right? You go this way this much and they're already looking the same. And so you can use them to a certain degree, but you have to watch out for symmetry, right? So the pop-out property here, again, illustrates that you can very quickly identify the outlier. However, you can sort of drown your pop-outs if you combine multiple dimensions. So this pop-out is quick to identify, this pop-out is quick to identify, but who has found the outlier in the third one? Okay. Okay. So the outlier's hanging out up there in the upper left. Sorry, I'll point you with my mouse, which I can't have access to. Oh well. Okay. So as you can see, this property called pop-out drowning actually occurs for many other kinds of pop-out as well. So you have to be aware of that. Let's talk about color. So color is one of my favorite topics in the world because it's so often misused by everyone. Okay. Even people who have really good intentions, like scientists, right? So scientists think that colors are perfectly orderable, right? So because they think, oh, the spectrum is just wavelengths and they go from short to long. So therefore, let's just let's map our scalar values, which we've got from our collecting berries and measuring plants, and map it to the wavelength, okay? Which is perfectly well-meaning, but what you end up is really groovy looking things like that, right? Very like, wow. The problem is, people are extremely bad at ordering colors, and there's no actual cognitive natural ordering that we think of when we see ordering. So I might ask you to order these colors, and you might just say, what? Which is the correct response. Because colors naturally we don't think of things in a particular way. If you want to prove to yourself that you're bad at ordering colors, there's a wonderful game called Color Monkey, which you can go play now if you had internet access. Darn, you don't. Okay. But basically, this shows that the level of agreement of color ordering is very bad, even if you're really competitive like this guy here. Another reason, second reason why you don't want to use color is that significant portions of a population do not have one or more of the receptors required to see color. So 8% of European ancestry males and 0.5%, the females definitely win here. A lot of us males cannot see, suffer from protanopia, which means that the second rainbow, it looks the same as the top rainbow. And that seriously affects your ability to see some things if you've mapped them onto the huge color scale. If you want to determine whether you suffer from any of these, you can identify which of the circles does not have numbers in them, because they all do. But the projector is a bit funny. The third reason why you don't want to use color, okay, why color is tricky, is that if you do map things to that linear spectrum, then you will pay most of your attention to the yellow things. There's a biological basis for this, in that our natural response to light is not linear. Okay, we've got rods and cones, two different kinds of sensors in our cells in our retinas, and they both have nonlinear responses, but they overlap in a region that corresponds roughly to yellow. So both sensors get very excited when you're in the yellow range. And they also have very different dynamics. So blue things, for example, we're extremely sensitive to blue light, but we can't focus on them because they're not in our phobia. And so we have this very, we were not designed to be linear response human beings. And so the result is that things that are in certain color ranges will appear much brighter. And I'll have a cool experiment which I'll show you here. So these two are actually the same data set. So somebody, a poor web science graduate student, went off and is plotting all the tweets here. Okay. So this is the length of the tweet. No, it's not. It's some other data set. But so this is the same data set. One is done in monochrome, and the other one is done in color. Now there are a couple of things to notice. The one in the color seems to be if you were to look for something weird or tendency for things to be similar or different, you might say, well, there's the red stuff down here, and then it gets yellow, right? We notice the hue changes very significantly. Whereas this seems to be a fairly even gradient as it's sloping off. You might also notice another thing which is very interesting is that with this blanket of green, there is not much detail in the difference compared to this version, where you can actually see the rippling effect quite a bit. So you can see subtle differences a lot more. That's because we are very sensitive to hue changes as opposed to slight changes within, major hue changes as opposed to slight hue changes. And so we hallucinate changes here, which are not significant, and are unable to see changes which are very subtle, right? And so this is a wonderful artifact of the fact that we're using different kinds of cells to look at things, and then we're going all the way broad spectrum. So that's another reason why you may or not want to use color in that way. Oh, pop-out drawn-out has another, there's another example where you can find the guy on the left pretty quickly, but you might be able to find the guy on the right pretty quickly as well. Yeah, it is, okay. So that was a bad example. But I'm not saying that everything in the world has to be black and white. You'll notice most of my slides are black and white. But and that there's a lot of good reasons to use color. And one of the safe things you can do is stick to one hue, right? And vary saturation, for example. But another thing people like to do is attach semantics to colors. So the map on the right is some country you may have heard of, and there's some significance to the coloring, which I can't tell you about because I'm American. But that's an example. Okay, let's talk about categorical data. Sorry, I'm just going to speed up a bit. So we've talked a lot about continuous value data, but you may be dealing with categorizing things in multiple ways. And one of the most basic types of categorical relational data you might end up deals with trees. Trees are often in everywhere. So hierarchical data can be very naturally and simply represented by trees. You can make them grow up from the bottom or top down. But if you have a very, very large tree, you might benefit from being able to zoom about it. So if you had an infinitely large tree, you could focus on one part of it and allow the individual to get to other places. This is a demo from 1991, the dark ages of computer science, and it was a Ben Schneiderman invention called hypermetry. But there are many other ways to look at hierarchical data. So this is what is called a tree map, which is sort of like taking that tree that we just saw and looking at it from the top down. So this, the top level boxes that you have are the first level children, and then the boxes inside that are the next level children, and so forth. And what you can do with interaction, we'll show you in the next section, is basically, if you're interested only in Texas, as everybody should only be interested in Texas, you can click on that and zoom into that section and then progressively go down. So Ben Schneiderman invented that technique in 1993. However, he was scooped 100 years earlier by this atlas, which did exactly the same thing. And this is available, actually. It's William Woodbridge. It's available as an open source thing that you can take a look at this beautiful atlas. Anyway, more on that later. Yet another way you can look at a hierarchy is by through these lovely diagrams called sunburst diagrams, where you essentially look at the tree at the root in the center, and with the successive leaves sort of in successive concentric arcs out from each level. Okay. And what's cool about that is that you can vary the length of the arc by a particular value of your choice, or even switch values if you like. But that's sort of getting into interaction, and we're going to save that for later. We already talked about this friendly thing, and this lovely friendly thing as well. But if you don't have a hierarchical data set, then you are dealing with the realms of essentially other kinds of things. Now, you might use your trusty friend, the Venn diagram, to display the relationships between membership in various kinds of sets. But it may also be profitable instead to use the generalization of a tree, a lattice representation, where any level can have more than one parent, and that can help you out. But one of the ones that we saw early on was what I was calling a parallel sets representation, which lets you then explore, and I'm going to show this to you now, because it also has local Titanic Southampton relevance. That basically places each dimension on a different line, and then lets you use selection to understand the relationships between the dimensions. What's neat about this example, though, is that you can actually rearrange the elements so that you can more easily see. So say that you wanted to understand whether surviving the Titanic would be better if you were in a particular class. And so let's move survive to the top and class up. It's a very controversial thing. And now you can very quickly see that there were, the relationship there. And so this representation then is, I don't know what else to say about it. But there's a circular version, which is often used as well. And that's what people call a chord diagram. What you've done here is you've taken each line and you've wrapped them to be one part of the circle. And there are these 3 examples that we'll talk about there. Animation, so if you have one of those, we talked about the multiple dimensions of data. If you had one of those dimensions as time, then a very natural approach might be to simply play your data through time. And so this is an example. All the flights that have taken off during a 24-hour period, this is real data, over North America. This is done by a student of Ben Fry's, so my mentor. His name is Aaron Copeland. He's quite famous now. But anyway, he was able to get a wonderful open data set and simply visualize the location of every plane. And you'll see that in the morning, a lot of planes take off on the East Coast. And you'll see the sort of the day sweep over as it becomes evening. And you can see exactly how crazy it is in the East Coast in the morning. Anyway, and this is great because people have these low-level perceptive abilities to identify motion. And so, but we didn't always have animation as an ability that we could quickly conjure up exploration data sets. So an alternative approach was taken by Edward Muybridge to discover that to convey the information that horses actually gallop with both feet off the ground. And this is what people call small multiples. So if you put a bunch of frames of your animation out side by side, then the eye is actually quite good at comparing 2 things that are side by side. And so you might use that technique instead. Who knows Napoleon's March?
Yeah, that's in maybe textbook, isn't it?
Yeah. Yeah. This is probably the most famous information visualization example in the world. And it's wonderful because it's extremely high dimensional, but it also tells a story. So this is not an example that people use to sense make. This is a narrative. This is a communicative example. And I'm going to ask you how many dimensions data set this is after I tell you what it represents. Okay? So the first thing this is a map, right? I'm not a historian, so you can correct my historical inaccuracies. But this is representing Napoleon's march into Moscow, and the map represents he was beginning in eastern France, I believe, and he marched. And this width, the light brown means that he was advancing, and the black means he was retreating. Okay, so that's one dimension. The size of the line represents the size of his army. Okay. And each branch of the army shows exactly where they went. So the little branch went off to explore at that point. But it's also a timeline. So the time of where the army was is represented along each point. Major waypoints are illustrated as well. And then during the retreat, it also displays the temperature of how cold it was at each waypoint on the retreat. It was a very rough time that he had as a result. There were very few people remaining. So how many dimensions do we have there? 5 or 6 is depending on how you count advance and retreat as being a dimension. And what's beautiful about that is that this is obviously not something that you can plug into Excel and get directly, but it managed to combine all of those information informative elements in a way that you can quickly see, things like the temperature may have had a major impact on the shrinking. For example, you see that really horribly bitter cold day, you see also marked with a significant shrinking of the line. And you can see that instantly, right? You don't even have to think about it. And so that's why this is a beautiful example, despite it being over 100 years old. The march was in 1812. Of course, this visualization was done in 1869. And this is another lovely example so they had extra space. This cartographer had extra space down here, and so decided, and really liked rivers. So decided to just compare the rivers. But what's really nice about it is not only is it the length of each river, but also exactly where rivers fork and split along their paths. By portraying them side by side like that, you can it really entertains you to sort of compare the rivers and identify how they intersect. There are 2 rivers that intersect there, which is lovely. And then probably my favorite is this example. Does anybody know, anybody who hasn't read Edward Tufte know this example? This is the French train schedule, Parisian train schedule, and each line here represents a station. Sorry, horizontal line, okay? And every tilted line is a train. And the vertical elements are the time. So this is 9 o'clock in the morning. You can identify which trains were at which stations, right? And the slope of the line there obviously represents the speed of the train. And so this, you could replace the entire timetable with this beautiful, abstract, modernist thing, and then confuse everybody, right? You know, you can use Waterloo, you should just put this up. You know, you'd be like, But what was the best thing, the best conclusion to this entire story is that when the TGV came out, their advertising campaign was to do that, right? So, that's just
So do they still use this? That type?
No, because everybody, tourists, wanted to kill themselves.
No, I mean the train planners at the background.
See, it would be really great if they then updated it for delays, so the train was like, you could see the lines move. Oh, that'd be
Because
amazing.
as a visualization, it's much better than a tabulated timetable.
And one of the students who's a web science student right now is actually responsible for realtimetrains.org, and he could definitely, for his master's thesis, good idea. He was actually my last lecture, and he lit up like a light bulb when I showed him that example, and he wouldn't sit back down. It was really embarrassing. Anyway, and so it was very good. So I'm going to show you. Do people know Hans Rosling? Okay, some people do already, but this will give me a chance to drink my coffee. And but anyway, so he's an incredible statistician, and he'll show you the power of narrative to visualization. This is a short version of his TED.
I got my video with Hans Rosling.
It was the last 200 years that changed the world. I will show you in Gapminder world here, the situation 1809. Each bubble is a country. The size show the population, and the color show the continent. The brown here is West Europe, and you can see from the map for the rest. This axis shows health, life expectancy at birth from 30 years to 80 years. And this axis shows income per person in dollar adjusted for inflation and for purchasing power. 200 years ago, all countries of the world had a life expectancy less than 40 years and had an income less than $3,000. Now I start the world. And you can see that the countries with good statistics are jumping up and down. There were famine years, there were better years, and West Europe and North America in industrialization started to grow the economy, but health didn't get much better. And slowly, health was getting better. And when we came to a situation about 100 years ago, most of the countries of the world had not improved much. It was only this part of the world that was getting richer and eventually healthier and healthier. And between the First and the Second World War, you can see that the difference between the richest and the poorest in the world is just increasing. It was after the Second World War that most of the countries started to change. The green Arab countries here get richer and richer. China here is getting healthier and healthier. Now economic growth starts in China also. And the Arab countries, the green ones, they get healthier. And here we are today. We have a continuous world from high-income countries with long life expectancy to low-income countries with very low life expectancy. But all countries of the world today has more than, or are estimated to have more than 40 years of life expectancy. And all does not have more than $3,000 per capita. So it means that the world has become healthier and richer. But the difference still is enormous between the richest country and the poorest country. And there are also very big differences within countries, which we cannot show here. But to show how the change came about in a different way, I would like to compare two countries here. I will go back to 200 years ago here, 1809, and I would like to compare the United States with China. Look, 200 years ago, the economy was growing in the United States, whereas it was declining in China, that was dominated by foreign powers. Then health started to improve in the United States, but nothing happened in China. And in fact, it was not until modern China emerged here, 1950, that China really started to improve. That was, of course, the great leap forward. That was what Mao Zedong called it. In fact, it meant a leap downwards. But eventually China got a better health and then started with a fast economic growth and is catching up with the United States. And today, the world looks like this. Some call it a flat world. It's not really flat. But what's meant with that expression is that the middle-income countries here, also called emerging economy, they have now a relatively good health, basic education for all, and some have very good education, are very capable, and they can compete with the high-income country in a completely new way, which we especially see now during the financial downturn. And in 2009, the income will fall in most of the high-income countries. It will be a very tough period for the low-income countries. Perhaps those will be worst hit by the financial downturn, whereas the middle-income countries continue to have economic growth, and the gap between the richest and those in the middle, that will probably shrink quite fast during the next 3 years.
He did a Boosie special, which is incredible. I'm sure you'll watch, and it's he actually has a full-size version. It gets on a ladder in order to point at things. But I know that I am running out of time because that's just the way things go. So I wanted to skip my other lecture, but just get to highlight a couple things. Is that all right? For about 10 minutes, and then I'll let you have coffee. Would that be okay? All right. I only saw one head nodding. It was Elena, so I'll assume that that's okay. So the other lecture, which is about making things interactive. And I just wanted to talk about why you might want to add interactivity. And there are four different kinds of reasons you might want to do that. And I want you to think about these four different things when designing interaction into your visualization. And that is, the reasons why people need to interact with something are often that they need to find something within something very, very big. And that's what we call finding. We're very creative when we come up with these terms for that kinds of activities here. But refinding is when you're trying to go back and find something you found before, so that awesome CD or book or fondue pot on Amazon. Discovery is the process of allowing people to find things that they didn't know they were looking for. Sense making, on the other hand, is simply what you might consider the science process, right? To try to understand relationships or elements between the elements or among the dimensions of the data that you're talking about. The last reason why you might want to make something interactive is to make it very engaging to people. So if you make something, you can make it personal or make it easier for people to relate to things to make it interactive. So I've given you that description, so now I'm going to give you a quiz.
I've got no address.
So what is Tom Cruise doing here? This is a wonderful movie. It's one of my favorites.
The Center Protection Team assumes we lock location.
Have you seen Minority? Okay.
Looks like federal housing, concrete and glass egg crates. Ouch. 1,000 rows in the district.
So he's got a very large data set that he's exploring, right? Which is memories that haven't happened yet.
9,
It's complicated.
6.
Okay. So any strong opinions? Is he doing it for fun? Is he doing this because it's just, wow, this is really cool? I would, first of all, buy a bed interface. Okay, so probably not fun. What is, any arguments?
Discovery?
Discovery? Why do you say discovery?
Resolving the world.
Well, I don't know the background, but is he trying to find something that he knows exists or something that he doesn't?
Right, so it might be that he's looking through the data set to try to see if there's something that he didn't know whether it was in there or not, but maybe he might come across something that might help him solve a mystery. So that might be an argument for discovery. Anybody else?
I'd go for sense making.
Okay, what is that?
Just to find a pattern in the data.
Okay, so he's looking for a number of things that lets him put things together. Anybody else? You might even argue that he was finding, right? Because he was looking for specific things, like where the crime or the thing that he was looking for happened, who the perpetrator was. So if you chose any of those three things, I would argue it was fun, and it was also fun. Okay, great. So now you understand the difference between those tasks. Okay, that was great, and that usually wakes people up. And what I wanted to do is then jump to a beautiful example and then let you go to break. These slides are all up online, and they have a lot of incredible links to great visualizations. But the one that I wanted to show you is a project that is actually what I think the most profoundly impressive demonstration that combines all of the low-level interaction primitives that we didn't talk about, pertaining to allowing to do those 4 tasks very easily. In a demo that Microsoft put together, and then canceled about a year later. Anyway, this is just a small excerpt from a TED Talk, and the system is called Pivot. And I remember the day that this came out, and I was still working here at the university. I was working, and I was blown away because I was working on a data exploration interface that did only a subset of the things that this does. So.
If I could leave you with one big idea today, it's that the whole of the data in which we consume is greater than the sum of the parts. And instead of thinking about information overload, what I'd like you to think about is how we can use information so that patterns pop and we can see trends that would otherwise be invisible. So what we're looking at right here is a typical mortality chart organized by age. This tool that I'm using here is a little experiment. It's called Pivot. And with Pivot, what I can do is I can choose to filter on one particular cause of death, say accidents. And right away, I see there's a different pattern that emerges. This is because in the mid-era here, people are their most active, and over here, they're their most frail. We can step back out again, and then reorganize the data by cause of death, seeing that circulatory diseases and cancers are the usual suspects, but not for everyone. If we go ahead and we filter by age, say 40 years or less, we see that accidents are actually the greatest cause that people have to be worried about, and we drill into that, it's especially the case from that. So you get the idea that viewing information, viewing data in this way is a lot like swimming in a living information infographic. And if we can do this for raw data, why not do it for content as well? So what we have right here is the cover of every single Sports Illustrated ever produced. It's all here, it's all on the web. You can go back to your rooms and try this after my talk. With Pivot, you can drill into a decade. You can drill into a particular year. You can jump right into a specific issue. So I'm looking at this, I see the athletes that have appeared in this issue, the sports. I'm a Lance Armstrong fan. So I'll go ahead and I'll click on that, which reveals for me all the issues in which Lance Armstrong's been a part of. Now, if I want to just kind of take a peek at these, I might think, well, what about taking a look at all of cycling? So I can step back and expand on that. And I see Greg LeMond now. And so you get the idea that when you navigate over information this way, going narrow, broader, backing in, backing out, you're not searching, you're not browsing, you're doing something that's actually a little bit different, it's in between, and we think it changes the way information can be used. So I want to extrapolate on this idea a bit with something that's a little bit crazy. What we've done here is we've taken every single Wikipedia page and we reduced it down to a little summary. So the summary consists of just a little synopsis and an icon to indicate the topical area that it comes from. I'm only showing the top 500 most popular Wikipedia pages right here. But even in this limited view, we can do a lot of things. Right away, we get a sense of what are the topical domains that are most popular in Wikipedia. I'm going to go ahead and select government. Now, having selected government, I can now see that the Wikipedia categories that most frequently correspond to that are Time Magazine People of the Year. So this is really important because this is an insight that was not contained within any one Wikipedia page. It's only possible to see that insight when you step back and look at all of them. Looking at one of these particular summaries, I can then drill into the concept of Time Magazine Person of the Year, bringing up all of them. So, looking at these people, I can see that the majority come from government, some have come from natural sciences, some, fewer still, have come from business. There's my boss. And one has come from music. And interestingly enough, Bono is also a TED Prize winner. So we can go, jump, and take a look at all the TED Prize winners. So you see, we're navigating the web for the first time as if it's actually a web. Not from page to page, but at a higher level of abstraction. And so I want to show you one other thing that may catch you a little bit by surprise.
He just shows off how you can view web pages in Pivot, which is a bit odd. But that example, there are many other examples in my slide deck that you can take a look at in your spare time, but illustrates the combination of very simple interaction methods, which were filtering, selection, and doing that in multiple dimensions, lets you, and you know, histogramming, right? We saw interactive histogramming, lets you immediately start to gain insights that would otherwise have taken you a lot of time and probably may have not arrived at unless you were specifically looking for them. So a good interaction design will help you perform discovery you know, of things that you did not expect to identify. Anyway, that is a very concise, accelerated version of the second lecture that I added on the first slide there. But I'm more than happy to answer any questions that you have during our practical. Meanwhile, we have some coffee, and I hope that was interesting.